Hey, welcome to the weekly webinar number 4 on PyTorch and Udacity GPU Workspaces. My name is Michael Floyd. I am your mentor and your mentee. You learn as much from me as I hope to learn from you. All right, so before we begin with the lesson, a couple of things about the classroom. Everybody's working on their projects, hopefully by this time. That is fine. If you still have not met with me to fill out your introduction form, still 5 out of the 14 people have not met with me. That would be great if you could set up that meeting. I'll be emailing you as well and requesting that you set up the meeting. And about the pace for this course. So what my hopeful intention was that nobody fall behind too early. Right now, only 3 people have completed the project, which means 11 of you guys are still doing the projects, which is fine, but I would really encourage to have more participation in the actual in the chat rooms. So you might be struggling or having a problem, just submit the problem. Maybe I help you with the problem. Maybe another classmate has the same problem and you help each other. Maybe somebody's already figured it out and does it. I'd like a lot more class participation going on. The like I said before, 30 minutes every morning, 30 minutes at night. Should be able to catch up and knock this out. And I said previously about a case of time spent with different students. So let me just repeat that. You have 3 students: student A, student B, student C. Student C is the student that we all wish we could be, right? Student C does not have a job, lives with his parents, and just has to trade his Xbox time for work on this down degree. But most of you, all of you, are within the student A and B categories, which student A and B, they both have full-time jobs, wives, children, but they're in this down degree program. Student A goes the route of inconveniencing everybody around him, sacrificing his time with his family, possibly sacrificing times where he might clean up his hygiene, whatever it needs to be. Student A gets the job done. Student B, however, works whenever is possible and hopes to complete the course. I hope all 3 students pass, but if I had any money, my money would be on student A. So just a choice between the type of student you could be. And now that that's said, let's get into the lesson. Let me share. I have to share this. All right. Okay, sharing the screen. All right, in the classroom for the lesson on PyTorch, I believe 8 different parts are given to help you guide you through PyTorch, and also your introductory steps into building a neural network, which is just a combination of different perceptrons. But as you can imagine, this is just something to show in part 1. As you can imagine, you start off with your inputs. You'll have multiple perceptrons and multiple layers, sometimes thousands within one layer of perceptrons. And your matrix multiplication, the weights and the biases, and eventually after all these layers and layers and layers, you end up with outputs. For the outputs, we have talked before, we use the softmax function for the outputs. And okay, that's similar to what it look like. But what I want to show you is more something that is already complete a lot of the things in the lessons on PyTorch seem to be not needed. They seem to be more, they guide you through the initial steps of how building a neural network and matrix multiplication behind this. But I would prefer to use the time to discuss actually, what your model will look like, and how to run your model, train your model, and the different things that will be needed for the actual project in this course. And after this, we will also go through a little bit through the project. I will not do that much of the project, but just show you, give the beginning implications of how you can proceed with the project. The project should actually not be that bad this time around as well. So let's start off with this code line right here. We have model equals classifier. Classifier is a class, and if we move up here, we have the classifier, and you initialize the classifier. And as we can see, we have 4 things already inputted into the classifier. These 4 things actually fully connected FCN. Well, FC stands for fully connected. These are fully connected layers. Okay, and what I want to show you here is you go from 784 to 256. So what this means is, since this is the fully connected layer number 1, this means we have 784 inputs, and those inputs will be fed into 256 perceptrons, or different layers. And those perceptrons, they have weights, right? 784 weights plus the 1 for the bias as well. And from there, from the 256, a part of the perceptron, that is layer number 1. And so from layer number 1, that is now our input that's going to be into layer number 2. So layer number 2 takes those 256 and uses weights to have 128 perceptrons. And the same thing happens after we fully connected layer number 2. We have a fully connected layer number 3, and that takes the inputs from the number 2, and from the inputs from the number 2, which is 128, it has 64, and 64 nodes or perceptrons. And from those 64, then another layer, but this layer only has 10. And this layer is actually our last layer. In this problem, we are actually given a data set, and the data set contains 10 different things. So we are using a classification problem to classify 10 different items. I think we have shirts, pants, purses, things of that nature. The name of the items are not important, but what our problem is we have a large data set, and from this large data set, we want to classify 10 different things that are within the data set. So, like I said, the last layer takes those last 64 and converts it into 10. And those 10 are going to be representing 10 different items in our classification problem. And from the for definition, what we have from the for definition is we have the initial shaping of our x. So our x taking in for the inputs, you have 784, which 784 is actually 28 times 28. The image is 28 by 28. And just to make sure you see this, 28 times 28 is 784. Okay, so the 784. Here it is. The 784 that we see in for the initial inputs is because we have an image that is 28 by 28 as far as the pixels in the image, and we're taking those and then we're running that into the neural network. So what we're doing initially, we're flattening out the pixels in the neural network, the shape. We have a one. Well, actually, since we are feeding in multiple images at the same time, we have the shape right here, which is the amount of images that you are feeding in, and you have the -1, which the -1 is the 28 times 28. And from there, we are feeding this forward. That's why they call it forward. We're feeding it forward, taking the X, applying the fully connected first layer, then ReLU activation unit, the fully connected second layer, and the ReLU activation unit. And this is a example of a forward pass where you have your X and you are feeding it forward to the networks, the weights and the biases, along with X give you L1, which is the first layer. Then you S activate it, and then you have your weights and your biases that give you L2, and then the L would be the softmax function, and then you apply it to Y. Okay. This is a bigger example of what a layer, actually this layer looks like. You have 784, 128, 64, and the output is 10. And this is what I wanted to show you actually. You have the sigmoid activation, the 10H, and the ReLU activation. And those are the differences between the activations. The ReLU is the quickest, but they all can be used to train the network. So using a ReLU activation, we've seen what our network looks like. We have applied the softmax, and that's our forward pass into the network. So that's explaining what our model does. Our criterion is how we define exactly the loss of our model. We are using the negative log loss function, which is a function to use, and we have the optimizer, and we are using Atom Optimizer in order to optimize the model parameters, and LR is the learning rate, which is 0.003. And so these are pretty straightforward, where it's going to be similar for each time you conduct a neural network in PyTorch. You're going to need a model, you're going to need a criterion, and you're going to need the optimizer that you use. The model will change based on what you are trying to predict, the amount of input layers, the amount of hidden layers, the size of the hidden layers, the number of outputs you need, whether that's 10 for this case or whether it could be 100. It can be a lot different as far as the model, but the criterion optimizer relatively can stay the same for almost all networks. So epochs is the number of times we go through the training data and train the model. And so we have epochs, and we have for E in range of epochs. And so for each epoch, what we're going to do is we're going to take the images and labels from the train loader, and the train loader is right here. The way the train loader is arrived is we are taking the data set that we are using, which the data set we are using is the MS data set. We are taking the training data from here, and we are transforming this data. So that's initially before we are putting in the train loader. We're taking the training set and transforming the training set. So as you can see here, we are transforming it to a tensor, which it is needed to transform into a tensor in order to conduct the matrix multiplication using the GPU quicker on the GPU workspaces. And we are normalizing the data so that it does not have any problems with regularization and can better train the model that we are using. So we are normalizing the data that you can see right here. And what we have the train sets after that. So after we transfer into tensor and normalize it, we have the training set. Fantastic. Now what the train loader does is it takes this training set and it shuffles it and produces batches of the training set each time you request the data from the train loader. So if there are 1,000 samples in the training set, instead of having thousands of images into memory, what it will do is now you are only taking 64 of those images and using those 64 of those images, and that is the loader. So each time you call the train loader, you are loading 64 of those images along with the 64 classifications. So you have the images and you have the labels that you are loading from the train loader. So as you can see here for images, labels, and train loaders, this is going to keep looping until the train loader is complete and the entire batch is called. And so what we have is we have the log PS, which is the you're getting the answers from the model. I'm not sure what I call it, log PS, and the log probabilities. But you're getting the answers from the model. So model, you're putting in images. So the images is what you were using. That would be your X. And remember, you are feeding this forward into the model, and what you are returning is the softmax of the first event, returning the softmax of all of the images, which would be the 64 images that are inputted into the model. You're getting probabilities, and you're using the criterion, the loss function, to find the loss, given the correct labels and the probabilities that are given from the model. And then you are calling your optimizer and back propagating which back propagating, what it does is it uses the derivative of the error to find the place where the to find the direction in which the error is changing the most, and based on that direction, moves the weight into that direction, giving the learning rate that we have had already, that we have arrived at already. The Atom Optimizer also changes the learning rate based on how the model is learning as well. So the Atom Optimizer is thought to perform better based on how the Atom Optimizer functions. And this is just an example of how it does that. So that's what this step does. It moves the weights in the steps that are moving towards the lowest amount of error using back propagation. So you are applying gradient descent in this step. As you can see, this is the training loss, which is a lot of loss. I don't know if the model is really training too well, but this is an example. So, and
and they haven't decided to tell you.
Same thing that we have just put over using getting a model. The model in this case, I think it's different. The model in this case is the same. And we're getting the images and labels similar to what we got right here. This is just getting the probabilities, using the exponent, the probabilities, and then just see which one is most likely. And then based on that, now you have the top probability. So let's slow that down. What these steps are doing is based on the probabilities output of the model. Remember, the output of the model, everything must be positive. So we take the exponent of the output of the model, and then based on which of the 10 has the highest amount, we then get, we can find the top one that has the highest amount. It can be 1 through 10 or however many, but you want the top one. And based on now you have the top one, set this equals, which is just the amount of things that are equal. You have the top class, which is the class that the model predicted, and you have the labels that are actually true. So all you're doing now is comparing what is predicted to the truth. And the reason why we're showing that is because we're using the equals to get the accuracy score, which you will determine where to stop the number of epochs and where to quit training based on your accuracy score that you receive from your models. This is just showing you, how to obtain the accuracy score. So now everything, and this is showing you can turn off the gradients. For example, if you already have a model, which I'll be showing later, if you already have a model that has been trained to do a different task, and you're taking in a model, you just want to change the a certain part and only change the weights and biases on a certain part, then you would turn off the gradients, which will be shown later. And so this is just another example. Your model, your criterion, your optimizer, your epochs are 30 now. Your steps are 0. And you have your training losses, test losses, which will be a list that will be shown. So you have E and epochs. So you go from 0 to 29. starting off with your running loss, and remember you have your training loader, so you're only loading the images and labels that you need. Your optimizer, and you are getting the probabilities from your model, your criterion, the same way that you did before, and based on that, you are backwards descending from the from using gradient descent, you're backwards descending, finding the highest slope that you can descend from that produce the best weights to change the probabilities in your model. And you have your optimizer, which is all just this step, same step, maybe different order of putting things, but just showing you the same step, and you're counting your loss, you're counting your running loss, and else you test loss, your accuracy is 0, and now so what you're doing in order to calculate the accuracy, you are turning off the gradients, and now you're looping through the test loader again. You are doing the same thing. You're finding the log probabilities, and you're finding the loss the same way. And here you're doing these steps that were shown above, right? You're taking the exponent, so with the exponent, everything now is positive. You're finding the ones in the top class, and you're saying your equals is the top class, whether that equals everything in the labels, which is just two arrays saying which parts of the array are equal. So if the batch is 64, you have 64 images, you're trying to see if which of these 64 is equal to the actual labels for these 64. So this will give you an array of size, 64, and that array will then be full of true or false. And since it's just full of true or false or 0 and 1s, then you can just say your accuracy is just the mean of that array of 64, which is just 0s and 1s, true or false. So you have your accuracy, and you're going to use that accuracy, and you can then using the accuracy, you will see exactly how your model is doing. And your trading losses, you're pinning your loss divided by your training loader, which is the average loss that you have per the average loss you have per run, or per run. So per each run be full of the average loss, and you have your test loss, which is the same thing but using the test loader. And then you print for each epoch. You will print epoch this out of, let's say this will be 1 out of 30 for the first epoch. You will print your trading loss. You will print your testing loss, and you will print the accuracy.
You should be averaging at least. You should be averaging like 12, 15.
So this is an example of what that look like. And as you can see here, our training loss for the training will always constantly decrease. But what you were looking for is the loss for the testing, to validate. Because if you do have a model that the training loss, your training data is fitting very nicely, but as you can see, the data you are not fitting on, which you're using as a validation, that data is not fitting. This means that the model is overfitting the training, and what you want is you want a better model that can also fit the training and the observations that is not seen. So, of course, the point of building any model is to make sure that it can generalize the observations not seen. And as you can see with the orange in this part, the model is not generalizing at all to other regions. It is not seen. So it's a phenomenon, overfitting. It can be dealt with dropout, L1 regularization, L2 regularization, and I will before we go into the GPU workspace, we have a little time. So we have part 7 and part 8, which is loading image data and transfer learning. In order to make sure we have time, I will do the loading image and the transfer learning while I'm introducing the GPU workspace. So, let me open these to make sure they are there.
All the time now. All the time now. Chill out. You're gonna say it. You're gonna make it all the time. Oh, hit it, and then somebody hit the buzzer. I'm calling it down. You see that? They're going to lob the taco.
That's crazy, buddy. That big.
He got body.
Okay, and here is the introduction to GPU workspaces. Make sure you read over this before you begin. So you have only 3 gigabytes of data that can be stored. You have the overview. This is how it's going to look like, just an IPython notebook. And the cool thing about the GPU workspace is you can enable a GPU. Remember, you only have a certain amount of time that you can use the GPU for. So you want to make sure that you enable it and disable it whenever you are not actually using the GPU. You only have 30 minutes of activity, and the 30 minutes of activity, after 30 minutes of inactivity, your thing will be terminated. And that is pretty much what I'm going to show you as far as that. Let's go to a.
Oh yeah, that was turn his draft.
I'm talking about after the game. What do you want? Why you ready to say that, man? Like,
can't finish. The problem is it should never be this low.
This is loading right now. I just wanted to load the workspace just to show you what the workspace is.
Everybody said, but everybody said that's what the issue was. They weren't consistent at the 3-point line, and that was gonna hurt them making a run.
Okay.
They must be reviewing that pushing them back.
All right, it's loading now.
What were we doing right there?
This is part of the first project. You have it's talking about image classifications. For the first project, what you're doing is using a data set of flowers. You have 102 different flower categories. You are loading, training, and the model in order to predict the flowers. So
Right now,
you have imports here.
Are you putting somebody?
This is where you will put your imports. The imports you can obtain from your parts that you're using. So everything you use is going to be the same. So if you're importing all these right here. You'll need these imports to your model.
He was gonna be a god. Oh, he was gonna be a god in the tournament. He was gonna
So,
be both of them.
and now we have the loading the data part. So we're using Torch Vision to load the data. You have your directories right here, your training directory, your validation directory, your testing directory, and you want to define your transforms, which I showed you in this part. Your transforms. It's how you transform the data. It's better seen here, loading image. So we have a little different inputs here. We're going to use the inputs that are here.
But it's hard when you tip it. When you tip it along. Oh man, you know how to know.
Going to paste the inputs here. We have the directories. What we want to do now is we want to transform. Looking back onto this lesson as far as loading the data, what we see for the transforms, you want to make sure all the images loaded are the same size. So what we will do is, what they do here is they resize each image to 255. They center crop, taking the middle 224 pixels, and then you are transforming that into a tensor, which is something similar, which is pretty much that we want to do for this image. So something like that. So just transform the data we're taking in. And this is just something else. Data augmenting is not really correct for overfitting. Is by taking your data, rotating it a little bit, horizontally flipping it. All these things are things you need in order to make sure you protect from overfitting. Hold on for 1 second.
The worst part is UCF is matched up well against them. I think either Liberty or Virginia Tech, they probably going to be Oh, well, Dominic, yeah. They just skip by the skin of their teeth on that. What else should we do for you? You doing straight sports or doing? Oh, you said the walk thing. Yeah, the walk thing, in and out. So, Mark, how do you feel about it? Did you feel good about a win like that or no? Right. Good about it. Otherwise, you just kind of think like scared and back up, right? You like, oh no. You did. I did. Oh no.
All right, I am back. Just to so this is a little thing like data augmentation. You probably need this for your project as well to augment the data. So you transform. Paste here. You transform. So you are transforming. This is just calling each group as far as transform. This will show you. You are resizing it, cropping it, and then making sure it is a tensor so we use it as a model. And then remember also, we have a training, validation, and testing set as well. So, for transform train, and you're going to want something similar for your validation and your testing that you will just rename valid and test. And you have your image data sets as well. And now you are loading in your image data sets. And so we're doing it the same way as here. So what you're doing is you're calling the directory, calling it transforms, and now you have your data sets that you are loading. So Control C, and Control V. And image data sets, remember you have your training, testing, and validation as well. So here's your training. And you want to make sure you're doing it on your transform train. Transform my S. So on your transform train. And remember, you have, well, instead of what you have used, you want to copy and paste. You have your training, valid, and testing set as well. And your data loaders is how you load data sets. So it loads the data in batches because it makes multiplication on thousands and thousands of images be a lot more complicated than just doing it in small batch sizes, and makes it easier on the computation for the CPU. So data loader, just go into here. This is the loading image data section. All we do is just copy exactly what it's doing as far as the loaded image data section. You copy, paste, paste the data loader. You have your data set, which is image data sets you were training.
You're gonna let it stop you.
And you have your batch size and shuffle. And that is it as far as loading data. What I'm going to do here is I'm going to insert a cell below this. And what they have here is you can see exactly an image and make sure that it's loaded correctly. So Control C, Control V. Now you're going to run your image. You have your labels. You have your data loader. And this is going to be train. This is going to be train. And you have your helper. I am showing your image normalize is false. Okay. So now if I run all these cells above,
What is that drawing?
and if I run this cell, what I will get is I will get an image, which is good. So we see we have the image that is what we needed. Okay. So we have the image that is what we needed. So now, since we know we have the image, we could do different things to our training data that the image is properly set up. So if you want to go back and you want to actually do things for data augmented, like rotating, horizontally flipping, all those things will help as far as preventing overfitting. And also, we actually need a normalized function in here. I believe so. Yes, right. If you actually read through here, it says, you got to normalize based on the mean or standard deviation as well. So we also need to normalize this data. So
going fast. Right for our lunch.
Yeah.
Tell you what though.
Yeah, she told me about that. Yeah, you would know you was today.
all right. So now we have normalizing. Let's just change the Control C,
So far, team played LSU.
Control V,
You know who goes to LSU? Savannah.
Control C,
Remember Santana? I think she
V, and that is us normalizing the data, normalizing, because the model is going to take the settings, we can normalize it for the valid and testing set. Remember, we do not rotate or flip the valid or testing set, because you should validate and testing. But you do need to normalize the valid and testing as well. So,
oh yeah, I'm straight up and down with it.
Just enough for them.
All right. So now for building and training the network, you're going to load in a pre-trained network, which is exactly what part 8 is. It is transfer learning. So a lot of neural networks that are already trained are used in order to train other networks, because training off of something that's already done is a lot easier, and it's pretty much the same weights that can be used, and very little effective output. So what we're going to be using is something that has been trained on the ImageNet data, and you have a lot of different models that are available in Torch Vision. This is Torch Vision. So you see here we have ResNet, LXNet, VGG. These are all the models that are there. Train. This shows you the error, top 5 error. And as you can, of course, it's what you would think. The higher the number of layers, most likely less the number of error, but also the bigger the layers, it takes the network a lot longer, a lot more time to compute computation. So this is it. All right. So transfer learning, we have this for importing, different imports as well for here. So make sure we have the imports that are correct. These imports, put them into put them into here, imports. We already have Torch. Network this anymore as well. So we have our imports. We're going to want to build and train the model. So here they pretty much do exactly what we did already. We have the training and testing, as you can see. They augment the data for the training, but they do not augment the data for the testing. And here you have the model that they're using. So Model S, that's called from, well, models, not Model S, it's models. Models from the flow. And we have DesNet, and we have 121, and that's what we're using, is DesNet 121. You can see that's DenseNet. DenseNet 121, so that's what we're using, DenseNet 121 in this example. So we are calling this model, and then we are putting model to see what the output is. This is the output for the model. What you have is telling exactly what's going in as far as the features and the different layers that are part of the layers. And these are convolutional networks, which we have not gotten into before, but convolutional networks have a window that slides over the image and also a pooling layer as well. I believe the lessons get more into that. But we have the value activation. And these are all the different layers that are occurring. But then after it goes to the convolutional, then it goes to the actually fully connected layers. You have these layers, all these different layers. You just go down to what I want to show. And after all the layers are done, what you now have is you have the classifier, which takes in the 1024 that is left from the image and outputs 1,000 features, which 1,000 features the ImageNet is 1,000 different things that it is training over. So you have 1,000 different features and 1,024 from 1,024 with the model. So this is the last layer, the classifying layer. Okay, so that is calling the model. So call the model would be something exactly similar to this. We just copy, paste, call the model, right? So we have the model, and we want to do this because we had a classifier that classified 1,000 features, but for this model, we have with what they are doing. They have two things they're classifying. I believe this is cat and dog. So what they have done is they have changed this classifier layer from taking the 1,024, feeding into 500, and from the 500, which is feeding into another layer of 2. So it's made 2 layers now. So it's going from 1,024 to 2, and those 2 will be like, I believe it's cat and dog. But that's something similar that you want to do for this model. We have 100, I think it's like 100, and I forgot how many it was. You have 102 flower categories. You want to do something similar. So take that classifier and change the classifier, whatever is inputting into the classifier, then output the number that you need into your model, which in this model will be 102 for our example. And that is how you would convert a model and also what you want to do for all the model parameters is you want to change the parameters that are in the model gradient, change the gradient to false, because what you want to do is you want to take the weights that are already associated with that model, and then based on those weights associated with the model, then determine if you can use that model to classify. So this is also an important step as well, is to freeze the gradient descent from the all the layers, all these previous layers, freeze the changing of the weights and biases, and only change the weights and biases for the classifying part of the model. All right. So that is what I'm going to show you, and in the lesson on that, make sure all right. Make sure you read over the introduction to GPU workspaces. One thing, GPU, it gives you GPU time. GPUs can speed up the computational process by upwards to 100 times faster than a CPU process. So make sure you're using the GPU when you train the model, but then make sure that you disable the GPU once the model has been trained in order to conserve your workspace time. Udacity does give you a lot of time, that's what it says, but you consume it. There's no guarantee whether you get more time. You use Amazon Web Services or something else in order to pay for more GPU time. Just wait for the CPU to computationally fix all that. But you don't want to wait 100 times more. So make sure you actually read the things to the workspace. Okay. Also, next week, Sunday next week, what I'm hoping is everybody completes the first project. That's the first project out of the way. And by Sunday of next week, I hope everybody has completed up to lesson 3 in the second part of this course, which is deep learning module. So lesson 3 is on training neural networks. So you need to complete lessons 1, 2, and 3. Most of lesson 1 I went over in the gradient descent. That was number 3 as far as weekly webinars, the previous weekly webinars. Most of the lesson and most what's needed to finish this next week has already been taught. And also we have new team leaders. Our new team leaders will be Hannah, Chandan, and Lucy. So hopefully Hannah, Chandan, and Lucy can fill in just as successfully as the previous three team leaders. And with that, are there any questions? I don't see any questions on the group chat. Possibly the group chat is doing something wrong, so I've never seen any questions in the group chat. But if there are questions, please post them in Slack at the moment.
Cracker Barrel has everything.
That's crazy.
And it's a whole little shopping center. I feel like Walmart was created on Cracker Barrel. Like Sam Walmart, we got pancakes.
I'll give you some time.
Yes. Well, they was big, something serious.
Okay, that's how we're after when I started texting you supposed to be in the video, I'm supposed to be in the video like you draw? Yeah, just talking to you about this. Okay, go. I still take my time. So, they never try to sign me up like that. No, I rep your week. For anything, you probably. I want you. Oh, yeah. Oh, yeah. I want hope.
All right. I guess nobody's gonna post. Oh wait, I do see a question. I believe I see a question. All right. Yeah, checkpoint for next week is while completing lesson 3. So I would like you to complete the train neural networks as well. If we go to the, let me save and checkpoint this. But if we go back, okay. So you have introduction to neural networks, which is pretty much, I believe that's most of what I did as far as that ingredients and most of what I did. That was also done in the week 3 webinar, and we have lesson 3, which lesson 3 is that's another hour. So we have an hour, and we have, I believe this might have been 2 hours or so, but in total that's 4 hours, which is less than 5 hours. I kind of was hoping everybody could complete. So yeah, completing lesson 3 is the goal for Sunday of next week.
It's not that bad. When we take our jersey, they like cover up the stars. Not that bad. Very sorry, straight. Then we can really only see shorts.
Yeah, I believe you. I'm just saying.
Thank you, Danny, for asking that question. All right, any more questions?
Wait, what time it close?
Lesson 1 is very large. How large is lesson 1? Okay, so if lesson 1 is very large, we'll just say let's complete up until lesson 3 for Sunday. Lesson 1 is very large. I will recheck lesson 1, but let's just complete up to lesson 3. So just 1 and 2. Lesson 1 is large. I'll also post exactly. I'll post it into the discussion boards as well as what is expected for next week. Yeah. All right then. So we'll just do lesson 1 and 2, and possibly just lesson 1. I will recheck that and make sure. But I will. So the goal for now is to complete only lesson 1 and 2. Okay. So that is it. Well, that is it for the time. It is 8 o'clock. Thank you for watching this, and bye. Peace.
Then they gonna know. Yeah. Oh, not too.